One good last math joke. I've got octopi here. 8-legged pie. All right. Last set of notes, Note Z, Module 12. We are looking at exponential and logarithmic applications. Good news here, you've seen most of these already. We've integrated them into the other sections as we've been going along. So some of this is going to look familiar, and then we've got a couple new examples in here as well. All right, first thing I want to remind you of is compound interest. Now, compound interest, we actually saw back in Notes V. So make sure that you refer back to those notes if you need a refresher here. And that Notes V was exponential functions. Okay. I do want to remind you what this formula was. It was A equals P times 1 plus R over N to the N times T. Okay. Now, that A value was your future amount. The P was my initial amount. The R was my rate, and remember the rate had to be as a decimal. So if they give it to you as a percentage, we're going to switch it over to a decimal. My N, which occurs in the denominator and this exponent, is the number of periods per year. And remember, we discussed that N equals 1 was annually. N equals 2 is semi-annually. N equals 4 is quarterly. And N equals 12 is monthly. And then the last piece here is T, which is my time in years. Okay, so just a little refresher there, but make sure if you want to peek back at an example again that you look back in Notes V. Okay, now in addition to compound interest, we also have what's called continuous compounding. Okay, when we look at continuous compounding, we are using A equals PE to the RT. We also saw this back in Notes V. If you remember, I had a little picture of a Pert shampoo bottle there. So the way I remember this equation, A equals PE to the RT, is thinking of that Pert shampoo. Okay. Now, new example for this, and it is going to be finding doubling time. Okay, so we want to figure out how long does it take money to double if interest is 3% compounded continuously. Okay, so key here is that it says compounded continuously. So we know right off the bat we're going to use A equals PE to the RT. Now, similar to our compound interest, A is going to be that future amount, P is my initial amount, E is E, R is going to be that rate as a decimal, and T is that time in years, okay? So those variables represent the same things that they did in compound interest. Okay, we want to know how long, so that means we are trying to solve for T. Does it take money to double? So that means we're going from my initial amount to twice my initial amount if it's 3% compounded continuously. 3% as a decimal is going to give us 0.03. So think about this. If my money doubles, I'm going to start with P And my future value is going to be 2p. And then we have e to the 0.03 times t. Notice I do not know what my actual initial amount was. I left it as p, but if it doubles, it's going to be 2p. Okay? Now, when I go to solve this, remember I'm trying to solve for t, the first thing I'm going to do is I'm going to divide both sides by p. Now I am left with 2 equals e to the 0.03 t. Okay, think about our exponential equations. The base on the right-hand side of this equation is e. Is there a way that I can easily rewrite 2 as a base of e? Nope. So I need to take the natural log of both sides. I'm going to have the ln of 2 equals the ln of e to the 0.03 t. All right, let's bring that 0.03 t down to the front. And I now have the ln of 2 equals 0.03 t ln of e. We know that the ln of e is what? Yeah, it's 1. So this gives me the ln of 2 equals 0.03 t times 1. But anything times 1 is that other thing to begin with. So we're going to have ln of 2 equals 0.03 t. We're trying to get that t by itself, so what's my last step? Yeah, I need to divide by 0.03. So I have the ln of 2 divided by 0.03 equals t. Now this is my exact answer. In order to get an approximate answer, we are going to make sure that we put this expression into our calculator. So I'm going to do the ln of 2, make sure you end that parenthesis, and then do divided by 0.03. And I get 23.10490602. So let's say approximately 23 years. Voila. There we go. All right, now we want to look at population or bacteria growth, okay? You're going to find that this equation looks extremely similar to our continuous compounding, that PERT equation. But notice that they've changed the variables a bit here. So instead of A, they're using N of T. Instead of P, they're using A. E is still E, and R and T are still R and T. Okay? So A is my initial population. R is that growth rate. It's still the rate. It's just a growth rate in decimal form. Still have to write it as a decimal. And T is still that time measured in units. So that N of T is going to give me my future population. Okay, let's include that in our little list here. N of T equals future population. Okay, so even though they've changed up my variables here, I really have the exact same equation still. So let's look at this in the context of a problem now. We have a population that's growing according to the equation P of T equals 1,600 e to the 0.16 t, where t is the number of hours. Notice here in this population model 2, they actually didn't use N of T, they used P of T. Same thing, it's still that future population. Okay. First thing they want to know is what is the exponential rate of growth? So if we look here, we are looking for that R value, okay? It is given to me here as a decimal, but it's going to be 16% as my rate of growth, okay? 0.16 would be fine here too. Either is okay. You've just got to make sure that if you write it as a 16, you have to have that percent there followed by it. All right, what is the initial population? Now we're looking for that initial population, which is going to be 1,600. How many will the culture contain at t equals 4? So what we're being asked to do here is we're being asked to plug in 4 for t. So we are going to have 1,600 times e to the 0.16 times 4. And this is something we're going to have to go back to our calculator to, okay? We're going to have 1,600 second ln, so we get that e to the something, 0.16, there we go. I was typing a negative in my calculator on accident, times 4. And we get 3,034.36947. And we're going to round that to approximately 3,034. Okay. Just pay attention to directions in a particular problem to see how you need to round your answer. Okay. Now, the last part to this question wants to know when the population will exceed 2,500. And it tells us to give our answer to 1 decimal place this time. Okay, so we need to take our equation and we need to set it equal to 2,500. So we're going to have 2,500 equals 1,600 e to the 0.16 t. All right, we want to get that base to my exponent by itself. So we're going to divide both sides by 1,600. And we get 2,500 over 1,600 equals e to the 0.16 t. Let's reduce that fraction on the left-hand side. This will reduce to 25 over 16 equals e to the 0.16 t. All right, so check out that right-hand side of my equation. I have a base of e. Is there a way that I can easily write 25 over 16 with a base of e? No way, Jose. So we are going to take the natural log of both sides. Excuse me. ln of 25 over 16 equals the natural log of e to the 0.16 t. All right, we're bringing that exponent down front. We get the ln of 25/16 equals 0.16 t ln of e. ln of e, remember, is 1, and 1 times anything is the other thing. So we're going to have the ln of 25/16 equals 0.16 t. So remember, that was really like 0.16 t times 1, but anything times 1 is itself. All right, I'm trying to solve for t, so my very last step here is to divide by 0.16. Let's see if I can squeeze it in here. So we end up with ln of 25 over 16 divided by 0.16 equals t. All right, we're going to put this into our calculator. And we should find that we get 2.7829, so on and so on. But we're going to round this to 1 decimal place. So we're going to say that it is 2.8 hours. There we go. So remember, because this is an application problem and it's asking me when, I have to make sure I put those units there. So 2.8 hours.